Today we're going to talk about a little bit more specifically about how the periodic table relates to atomic structure and bonding. Just a little review for our atomic unit. Most atoms want to have 8 valence electrons. Of course, the exception is smaller atoms, which really can only fit 2. Atoms can gain or lose electrons by bonding. They can also share electrons as well, which we'll talk more about in our bonding unit. But right now it's kind of easier to focus on the ideas of gaining and losing electrons. The outcome is the same, trying to have 8 valence electrons. Having a full valence shell can be called a noble gas configuration. Sometimes another statement that's sometimes used is a stable octet. So just a little review for you. If we were looking, for example, at sodium, so sodium's electron configuration is 2, 8, 1. Sodium, in order to get 8 valence electrons, is going to lose that outside electron and now have the configuration 2, 8. So our atoms configuration is 2, 8, 1. Our ions configuration with that +1 charge is 2-8. So if we look at fluorine, fluorine's configuration, we have a total of 9 electrons. So we have 1, 2, 1, 2, 3, 4, 5, 6, 7. And then when fluorine forms an ion, the easiest thing for it to do is gain an electron and become 2-8. So what you're going to notice here is the configuration of a sodium ion is 2-8. The configuration of a fluorine ion is 2-8. Even though they form different ways, they actually one formed by gaining and one formed by losing. If you look at the periodic table, you're going to notice that neon has this configuration as a neutral atom. So this is actually something we call being isoelectric or isoelectronic. Isoelectric species are atoms or ions with the same electron configuration. So if you go to example for krypton on the periodic table, if you look at krypton, in order to figure out who is isoelectronic with krypton, we would want to figure out who would have the same configuration when they have gained or lost electrons. So we're actually specifically looking at ions here, and we do need to write them with their charges because that's when they actually become isoelectronic. So one example for this would be selenium, Se, with a -2 charge. So its usual configuration is 2, 8, 18, 6. When it gains 2 electrons, it becomes 2, 8, 18, 8, which you will notice is the same as krypton. Br -1 is isoelectric with krypton as well. So by gaining 1 electron, bromine will have the same configuration as krypton. On the metal side of the periodic table, rubidium. So rubidium's configuration is 2, 8, 18, 8, 1. Rubidium loses an electron to become a +1 ion. And again, we get krypton's configuration again. Strontium +2, yttrium +3. You can kind of go on and on, but you just need to be able to name a few of these. It is important to note that if you just write bromine or, sorry, I shouldn't have moved that. If you just write bromine or rubidium and you show them neutral, in that case, they are not isoelectric with krypton because they won't have the same 36 electrons that krypton has. Bonding is also heavily influenced by something called effective nuclear charge. We have talked about nuclear charge before. This is the charge of just the nucleus in an atom. In other words, it's really the same thing as the number of protons. So if you go to oxygen on the periodic table and you want to know oxygen's nuclear charge, oxygen's nuclear charge is +8 because there are 8 protons in the nucleus. Now, effective effective nuclear charge is a little bit different. This is the net positive charge experienced by a certain electron in an atom. Typically, in our purposes, we're going to be talking about an electron in the valence shell. So this is the net positive charge felt by a valence electron in an atom. Effective nuclear charge is influenced by two main factors: the number of protons in the nucleus and the number of PELs in the atom. Larger atoms that have more PELs, those outside valence shell electrons, are going to actually experience less of the pull of the protons in the nucleus. So the inner electrons can be called kernel electrons. We're going to use that term. I won't test you on it specifically, but you do kind of need to understand what that means. And kernel electrons actually create something called shielding for valence electrons. It is as if the inner electrons are almost blocking the outer electrons from feeling the charge of the nucleus. So this is especially as an atom gets bigger going to influence its ability to gain or lose those electrons in the outside rings. We can actually calculate this by taking the number of protons and then subtracting the number of non-valence or kernel electrons. So the effective nuclear charge, ZEF, is found by protons minus all the electrons that are not in the valence shell. So let's look at a little example here. If we look at sodium, where we have our 2-8-1 configuration. Sodium has 11 protons minus, in terms of non-valence electrons, we're not counting the outside one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sodium has an effective nuclear charge of 1. I should really, truly actually say positive 1. If we look over on the other side and we look at chlorine, which is 2, 8, 7. So we're going to do our number of protons minus our non-valence electrons. So 2, 4, 6, 8, 10. This gives us an effective nuclear charge for chlorine of positive 7. Now, based on this, what we can actually determine is which of these atoms will be more likely to lose a valence electron. So if you look at the configurations, which we've done so far, you can make a good prediction that that's going to be sodium, because he only has one valence electron. The reason that this is sodium, the reason that that works the way it does, is because of effective nuclear charge. So the effective nuclear charge of sodium is only +1. So sodium will lose an electron because there is less effective nuclear charge pulling on the valence shell. So this is actually kind of the explanation, the atomic structure explanation for why we actually have the octet rule. If you look at the effective nuclear charge for chlorine, this +7 here is being felt by any electrons in that outside ring and any other electrons that come nearby. So if you have a valence electron in sodium, and then it sees a chlorine, so chlorine can kind of pull that electron away because that higher effective nuclear charge. Now, it's nice to compare these to electronegativities and ionization energies. What you're going to notice is electronegativity, remember, is that strength, that ability to hold electrons. Ionization energy is the amount of energy it would take to remove an electron. These are going to be lower when you have a lower effective nuclear charge, whereas in chlorine, the higher effective nuclear charge means it's going to be a lot harder to lose electrons. They're going to be more likely to be gained.